important thing we have learned is that we have learned something called orthonormal basis. For any quantum state, we can express them as a linear combination of some basis states, right? Like what we said in a 3D space. This is easy to understand, right? For any vector, we can express as, for example, v, right, equal to ax x hat plus ay y hat plus ac c hat, right? And of course, now we're talking about the complex space, which is a more general Hilbert space, but it doesn't matter. We need to represent them as the linear combination of some basis states. So in this particular case, the basis states are B0, B1, all the way maybe to Bn minus 1, right? Just like in 3D, we have x hat, y hat, z hat. Now we have B1, B0 all the way to Bn minus 1. So this is an n-dimensional space. It is more convenient, and we want to do that also throughout all the quantum computing exercise, that we will choose an orthonormal basis state, which means that when I is not equal to j, means you are not the same vector, their inner product is 0. This means they are orthogonal, right? This means they are orthogonal, right? And if they are the same, that means just the inner product to itself, we want that to be 1, which means it is normalized. Okay, that's why it's called orthonormal basis. This is not difficult to understand if you try to think about the real 3D space. X hat dot x hat is 1, but x hat dot y hat is going to be 0, right? We also want to work on the normalized vector. So for example, if I have a vector written in this form, but again, when we write it in a matrix form, in a column form, we need to remind ourselves A1, A0 refers to the amount of the basis state of whatever. Here you can call it B0 or call it zeros or call it other name, but that is the first or zeroth basis state, right? So this one I number it from 0 to n, so it's n plus 1 dimensional space, right? This refer to I have an part of Bn, right? A normalized vector will satisfy this definition that their inner product has to be equals to 1, right? So I hope that you remember how to do the inner product. When you convert a vector from the cat version to a bra version, you need to put a complex conjugate, and you just do an inner product like this, right? Becomes A0 star all the way to AN star, inner product with A0 all the way to AN, right? I hope that you are very familiar with this. We also talk about how to change the basis, right? Again, like what the example I mentioned, I buy 12 eggs. You can say I buy 1 egg. Each egg is a basis, right? Or you can say I buy a dozen of eggs, right? So a dozen egg is the basis. So this is the simple example of changing basis, right? So we can have a 0 and 1 basis. Later it will be clearer what we're talking about. Usually we call it the computational basis. And we can also have plus minus basis, right? Now we just treat it as given, right? But last time we also learned that it can be just a transformation of the Hadamard gate, right? We'll review it later again, right? And if I know this basis 0 equal to a linear combination of plus and minus in this way, and 1 is plus and minus in this way, then I just need to substitute and then do the grouping. I have successfully changed the basis from 0 and 1 to plus and minus. Now, just note that they are equivalent, right? But when I write the matrix form, so it will be a column vector, it will be written as AB. While in this case, it will be written as 1 over square root A plus B, 1 over square root 2 A minus B. Why? For the same vector, we have different entries. Again, whenever we write in a column form or matrix form, we need to remind ourselves what are the basis states. In this case, it say I have A part of 0, I have B part of 1. And this case is 1 over square root 2 a plus b part of plus, and this is that much of minus. Okay, so remember this, and in that case, these are the same. Okay, so we learn about the changing of bases. Okay, so just try to review, make sure you understand these basics. Right? In the last video, I also showed the reference to my book. You can take a look. We also learn about the quantum gate. We start with some very simple quantum gate, right? The NOT gate. The thing I want you to memorize, really memorize, is that a quantum gate is defined by how it rotates the basis or it changes the basis state. So for example, for a NOT gate, we say that it is by, the definition is I apply the NOT gate equals to 0 state, then it will bring me to the 1 state. And if I apply it to the 1 state, it will bring me to the 0 state. A more concise way is that x on a can be 0 or 1. It gives me the negation, right? The not of a, right? So that is the definition. And we also have the corresponding matrix, like written in this form. I suggest you to memorize it. We also learn about the control NOT gate. Maybe I jump a little bit, come back later. Let's finish the 1-bit phase shift gate. Looking at this is the matrix. But by the definition is again, what is the X gate, right? It is that X applied to 0, you do nothing. It means you have an identity operation to the first basis vector. But if you apply this to the second basis vector, then it will append a phase of e to the power I phi to it. Okay, then for example, if there we have 3 very special gates when phi equal to pi, e to power I pi is -1, right? So do not mess up this. I really want you to memorize this Euler equation. Right, e to the I phi equal to cosine phi plus I psi phi, right? So if phi is pi, this is 0, this is -1. So you get this something called Z gate, which is 1, 0, 0, -1. Okay, and we also have the S and T gate, basically T squared equal to S. For their matrix. Okay, and then S squared equals to Z. Okay, now there's another very important gate that has no classical counterpart, which is the Hadamard gate. What does it do? Just based on the definition, H applied to 0, what do you get? You get a linear combination of 0 and 1. And what is linear combination? It is superposition, right? Again, we say many times, quantum computing is the same as classical computing if you only operate on the basis state. But now, what it is special is that it has superposition and it also has entanglement, and that is what it makes it so powerful, right? So in this case, Hadamard gate is a gate that can help us to form superposition, and this is the matrix. And a very special thing about Hadamard gate is that it is its own inverse. In other words, it also means that H times H equals to the identity gate. This is useful sometimes when you use to simplify a quantum circuit. These are the 1-qubit gate. And the last part of the last lecture, we talk about the 2-qubit gate, the C0 gate, or the exclusive OR gate. Okay, so let's maybe I actually not going to review this. I will review when I continue on the 2-qubit gate. Okay, now we also learn about the tensor product. If we have 2 qubits or 3 qubits or multiple qubits, what we are doing is to combine or to form a larger space from a smaller space. Right? You may have a 1 qubit belongs to the Hilbert space 1, another qubits belong to the Hilbert space 2. If you combine them together, it is something called tensor product, which will give you the Hilbert space 3. So this can be like a 1 qubit. We call it C squared because it's complex, right? Two-dimensional complex space. If you do the tensor product of them, you are going to get complex, a 4-dimensional complex space. Okay, C to the power 4. How do we do how do we form a larger space? Now for vector, I did not say here, but you can think about that. If I have vector that is AB, another vector is CD, then when I do the tensor product, it is very easy in terms of methodology. It is just that I can do this in this way. I just multiply it inside, or basically I do all the permutation. And this gives me AC, AD, BC, BD, right? That is how I form a larger space. And if I have a matrix, n by n, how do I do that? Again, I take every element from the first matrix and then multiply by the whole matrix of the second element. Okay? And then I just do all the permutation and to get the combined matrix. So this is n by n, and this is n by n matrix, right? So after I multiply it, what do I get? I get n squared by n squared matrix. Okay? Am I right? Yeah? N times n, right? Okay? So that's what we learned last time. So let's continue. Okay? Continue on the multiple qubit.